For two vectors, small f and small g, with a length of n, we let capital F be the discrete Fourier transform of small f and g be the discrete Fourier transform of small g. Then we let h, vector h, be the element-wise product between f and g from 0 to n minus 1. Then now the discrete convolution theorem states that the discrete convolution between f and g will equals to n multiplied by the inverse discrete Fourier transform of the vector h over here. So the purpose of this video is to actually prove that, Okay, so we're going to start with the definition of discrete convolution that we were using previously, right? Between f and g, let's use the lth, component here. It's the sum between from k is equals to 0 till n minus 1 of f subscript of k multiplied by g subscript of l minus k over here. Okay, in order for us to prove this, first and foremost, k is equals to 0, n minus 1. Can you see that? N minus 1. Okay, we are going to express f subscript of k in terms of the inverse discrete Fourier transform of capital F, right? So it's going to be sigma from n is equals to 0 to n minus 1, right, of capital F e to the 2 pi I n k over capital N, right? We are going to do the same with g subscript of L minus k. Then for this one, we're going to use m is equals to 0, factor m to the n minus 1 of capital G e to the 2 pi I m. Instead of k now, we've got L minus k, right? So at this point in time, we are going to rearrange, the sums together. Then we've got k is equals to 0 till n minus 1. Then in front of this sum, we're going to have this e to the power something. So it's e to the power 2 pi. I forgot the divide by n here. 2 pi I n k divided by n multiplied by e to the power 2 pi I m. Let's just multiply the m times l, ml minus 2 pi I m k, right? And then I'm going to multiply that with sum from n is equals to 0 to n minus 1. This is divided by n. Even this here is divided by n. Okay, f n, capital F. Then we've got here capital G from m is equals to 0 to n minus 1. I trust you guys can appreciate that. Then at this point in time, guys, we've got similar bases here, so we're going to add the exponents, right? Okay, so sum between k is equals to 0 to n minus 1. So when we add here, everything's going to be divided by n, right? So this is e to the power what? It's 2 pi I n k plus 2 pi I m L minus 2 pi I m k. All of this we divide it by n, right? Then this one remains the same. The sum from n is equal to 0 to n minus 1 of fn, capital F of n. Then even this one remains the same. From m is equal to 0 to n minus 1, right? Then now, this side, we're going to sum from k is equal to 0 to n minus 1. So we are going to take this portion, the other side, you know. How we're going to do that? We're going to do it in this manner. It's going to be e to the power 2 pi I n k minus 2 pi I m k. Then e to the power 2 pi I m l, we're going to take it to the other side. The sum of f n is equals to 0 to this divides by n here, right? And then minus 1 from m is equals to 0 to n minus 1. We've got g of m e to the power what? E to the power 2 pi I m l over here. Okay, so divide by n, sorry. We divide by n over there. Okay, and then when we continue, this equals to, let's simplify further on the first portion. K is equals to 0 to n minus 1 e to the power 2 pi I k n minus m. So I want you guys to take special attention of this over here. This over here. Right. This is divide by n. And then the sum of f n is equals to 0 to n minus 1. Okay, so this remains the same. M is equals to 0 to n is equals to 1, n to the minus 1. G of m e to the 2 pi I m l over n. Okay, guys. So now, if you look at this sum over here, this sum was proven that if m equals to n, then the sum equals to n, right? Otherwise, this sum, the sum equals to 0. Okay, so I might also do the proof that actually shows that. So basically, we are going to use this condition here. So m equals to n in this case. We're gonna continue from there, because if it's the otherwise part, everything is going to equals to 0, you know. Okay, guys, so our proof now boils down to the fact that the sum from n is equals to 0 to n minus 1 of the capital F here Now multiply that with the sum of n is equals to 0 to n minus 1. Capital G there. E to the power 2 pi I n L divide by n. Multiply everything by n. Okay, and then let us simplify further and put this and this into the same sum. Okay, so from n is equals to 0 to n minus 1 of fn gn e to the power 2 pi inl divided by n multiplied by n. All right, this sum, guys, corresponds to the inverse discrete Fourier transform, right, of a vector whose nth element is fn and gn. As you guys might recall from above here, that vector h, this was the element wise product of f and g from 0 to n minus 1, right? So basically we have arrived. So this here is our h, right? But for the nth component multiplied by n. So voila, we have arrived at what we're requiring. And just to take note that h of L, or h is the inverse Fourier transform of this guy over here, you know? So we have actually proved, guys, that we have proved the discrete convolution theorem equals to n multiplied by this over here. So we have proved this successfully. If you can also look at the definition over here. So I suppose that is satisfactory. Do let me know of any uncertainties. Have a blessed day.